Okay, so just one announcement to join the class via Zoom. There will or watch the Zoom recordings. You can also access them directly from the web page from now on, instead of logging into CCLE and then you going via that link. But you'll need a password, which is going to be 36 Turing. I think all lowercase. Okay. All right. So last class we talked about what the course is about, how we're going to do the various things, and we started asking this question of how do we actually represent data on computers. And we said everything at the end of the day is just a binary string. And then we define this notion of encodings, right? And we saw encodings of integers, of natural numbers, and we came up with a nice, clever several suggestions, several solutions suggested by you on how to even represent rational numbers on a computer. Okay. So today, what we're going to do is to take this discussion further and talk about how we can automatically compose representations. And this will lead us to this very important concept called prefix-free encodings. And hopefully, if we have time, we'll go on to the next section, which is circuits. Any questions about last class? Okay. And please feel free to interrupt me at any time with questions. One of the best things about in-person teaching is this interaction, right? So let's maximize that. So last class, we saw how to represent rational numbers, right? So basically, we saw an encoding from the set of rational numbers Q to 0, 1 star, the space of strings which have only 0 or 1 entries. Okay. And today, what I'm going to do is present a slightly different encoding, which achieves the same thing. But this will have the advantage that you can actually generalize it further to not just rational numbers, but any kinds of pairs of things. Okay. So to do that, I want to first introduce a new encoding for integers. So let's think of what we did for rational numbers, right? If I had to encode P by Q, the simplest way would have been to maybe do encoding of numerator, concatenated with encoding of denominator, right? This was the simplest thing we could have done. But there was a problem with this, which is that if I just see the string of the concatenation of the encoding of numerator and that of the denominator, is that good enough for me? No, right? Because I don't know where the numerator ends and the denominator begins. So there's nothing in the string which is marking the end point of the first element, the numerator, and the beginning of the second point, right? So today what we're going to do is to change the encoding of integers so that we can actually tell this when the encoding of some integer ends and the next one begins. Okay. So here's a new encoding. Let me call it Z to S from integers to 0, 1 star. S is a space of strings. Basically, S just means you have 0, 1 star strings. And what this is going to do is take your old encoding, replace each 0 with 0, 0, replace each 1 with 1, 1. I'm doing something silly, which is I'm kind of duplicating the encoding, right? I looked at my old encoding, which you saw, like, let's say you're using binary representation or something like that. And I'm just duplicating every symbol. If you had a 0, I'm kind of putting 0, 0. If you had a 1, I'm putting 1, 1. But now I want to use this to help me tell when the encoding of a number ends and when the encoding of a new number would begin. So what else can I do to make that happen? Yeah. Encoding integers. Yeah. Take your old encoding. That's a good question. I should be clear of integers. Yeah. Exactly. Right. So replace each 0 with 0, 0. All right. Something simpler will also work. End with 0, 1. Okay. This is my new, let me say, Z to S bar to distinguish it from the old one. Right. So let's do an example. So what was our old encoding of integers? If you had the number 1, we first said, we're going to use 0 or 1 to tell the sign of the number, right? 0 means sign. And 1 in binary was just 1. Okay. So what would the new encoding be? 0 will become 0, 0. 1 will become 1, 1. And then I get 0, 1. Okay. Now, similarly, let me just do one more. So Z to S of, let's say, -3 would have been 1 to say the sign. And then I would have 1 and 1 at the number 3 in binary. Right? This is sign 3 in binary. So Z to S bar of -3 would be 1, 1, 1, 1, 1, 1, 0. Okay. I mean, it looks, unnecessarily redundant, right? Just duplicated everything and then tagged along the 0, 1. Right? But now there's this advantage that I can always tell when the encoding of a number ends because it ends with 0, 1. Right? So given this, I can find a new encoding. How can I get a new encoding of rational numbers? Let's say Q to Q, Q to S of rational numbers, 2 strings. What can I do now? Well, I can just concatenate. The simple solution that did not work before will work now. Right? Earlier, I couldn't do just encoding of numerator and then encoding of denominator, but now I can do it. Right? Any questions about this? All right, but let's just make sure we are correct and show that Q to S is a valid encoding. So how can I show that this this specific encoding Q to S is a valid encoding, I need to show it is 1 to 1. Okay. How can I show it is 1 to 1? Well, one of the simplest ways is to actually show a decode. Given my encoding, I'll show how to get back the original rational number. And that's proof that if you have it, I mean, if you have a decoder, then you should be 1 to 1. Okay. So let's say, let us write a decoder for Q to S. So let me call it S to Q. And what should this satisfy? S to Q of Q to S of P by Q should equal P by Q. Right? So that's the decoding property. When I look at the encoding of a number, of a rational number, and apply the decoder, I should get back the original rational number. So how can I decode? Given the string, which someone is saying is the encoding of a rational number, how can I get back the rational number? Any suggestions? Well, it's not that complicated actually. So you keep reading. Again, think as if you're a programmer, right? So I gave you a binary string and I'm asking you to decode to the actual rational number it represents. How can I do that? I'm going to keep reading the input string. You gave me a sequence of zeros and ones. Input string, 2 bits at a time. Okay. I keep reading first 2 bits, then third and fourth, then fifth and sixth, and then 7 and 8, and so on, until you see 0, 1. Right? And once we see 0, 1, what do we know? We know that we have found the end of the encoding of numerator. So we can just use that. Once we find 0, 1, everything before is encoding of numerator. Everything after is encoding of denominator. Okay. So once I can do this operation, I can recover the original numerator and denominator. So this is a valid encoding because I have a good decoder for it. Does this make sense? I mean, this seems like a more cumbersome solution than the ones that you suggested in last class. But as we'll see, this has some merit in that we don't have to be that clever about it. It's a very mechanical way of getting encodings of tuples. All right. That's what we are trying to do. Kind of somehow maybe make it automated instead of trying to be clever for having to come up with new encodings. All right. Okay. Let's do one more example of this. So example. So what would be the encoding of, let's say, the rational number 1 by 2, right? So this is going to be z to s bar of 1 to z to s bar of 2. And 1 is 0, 0, 1, 1, 0, 1. You can check that. And 2 is going to be 0, 0, 1, 1, 0, 0, 0. Okay. So why is that? So let me say z to s bar of 2 is So 2 is just 0, 1, 0. The sign is 0, and then its binary representation is 1, 0. So you have to replicate every one of those. So you get this guy, and then you end with 0, 1. Okay. Any questions? So let me maybe write this properly. Yeah. Yeah. So hopefully it will become clear now in what I'm going to say next. But this, do you at least agree that this is one other way to encode rational numbers? Okay. Maybe it seems like not the best solution so far, but it is definitely a solution, just as we saw before. So the question is, there a link to these notes? You can watch this note. There is a link on the course website under course notes. If you go there, you'll be able to access it. Any other questions? That's a good question. We'll get to why we are doing this in just a second. Yeah. Right, so that's one way to think about it. I mean, it could serve that purpose as well. But here, our purpose really was to kind of find a way to mark the end of encoding of one number and start of the other, right? So here, if I just show you the string, you can keep traversing 2 symbols at a time, and immediately you know where the encoding of the first one is, right? Which is might not be easy to do if you take other encoding. Okay, yeah.
Because we know like where an encoding stops, right? We have 0, 1. So why are we adding the 0, 2, and 5?
Oh, if you don't duplicate and we just added 0, 1 in the end, we won't be able to tell when an encoding ends, right? So for example, that's a good question. Why duplicate and not just add 0, 1 in the end? Right, that's your question? No?
Here, I think we are encoding font, right? In Z2S font. Why are we adding the 0, 0, and 5?
Oh, that's just for the sign. Right, right. You could have 0, 1 or -1, right? That's why. Yeah, that's a good question. But let me answer my own question, which is, why are we duplicating and not just adding 0, 1 in the end to help me tell when a number ends, when the other begins? What could be the problem if I just don't do the duplication? Yeah. Exactly, right? If I take the encoding of the number 5, its encoding is 101. So once I see 0, 1, should I just cut off there? No, right? Because it can cause ambiguity. Okay. All right. So we will exploit, basically extrapolate from this idea to get something very general, which is, give me a representation for any object. I can construct representations for lists of those objects. It's a very powerful primitive, because once you can do this, you can recurse. All right. So what did we do here? What we saw was we went from representation of integers to representation of pairs of integers. Right? A rational number is really just a pair of integers. Okay? So we took a representation for integers, and we got a representation for pairs of integers. But what if someone comes and says, give me a representation for triples of integers? What do I do then? If it comes and says, give me a representation for maybe a list of integers, all your scores, how do I represent them? Right, so we can do that. And because we can do that only because we did this duplication in 0, 1. Okay. So let me abstract this concept. So what's so special about this duplication and ending with 0, 1 is that it satisfies one very nice and stringent property called prefix freeness. Okay. So we have, there are encodings that we can use. There are many, many encodings. Among all the encodings, you can look for all kinds of metrics, how good are they in terms of error correcting, length, and so on. But one really nice property is prefix freeness. So what is that? Suppose I have an encoding, I have some objects, I'm mapping them to binary strings. We will say this encoding satisfies, is prefix free if the following holds. Essentially, whatever this, it's right there in the name. Prefix free means that if I take the two encodings of two distinct objects, neither one can ever be the prefix of the other. More formally, for x not equal to y in theta. If I take two distinct x comma y, then e of x is not a prefix of e of y. Okay. So imagine that I have my object x, my e gives me a binary string. And I have my object y, it gives me maybe a longer binary string. Okay. But prefix freeness means that the encoding of x cannot occur as kind of the beginning of the encoding of any other object. All right. So if I sort of imagine looking at this part, these two should be distinct. Okay. Being a valid encoding just means that e of x is not equal to e of y. Prefix freeness is stronger. It's saying not only are they distinct, but one can the beginning of the other encoding. Make sense? Okay. So let's look at the examples of, we saw some encodings already, right? Let's think of n to b, the encoding of natural numbers to binary representation that we already saw. Is that prefix free? No, right? Can you give me a counterexample? Yeah, so if I look at n to b of 1, it's just 1. N to b of 3 is 1 and 1. Okay. So binary representation, even though we think of it as the most basic representation, is not prefix free. It's not a very good representation because of that. Like, once I start seeing the string, until I reach the end, I don't know what number it is. Okay. And You can find such counterexamples everywhere. How about Z to S bar? We just saw what that is too, right? Is that prefix free? Yes. And we'll see why in a second. We'll actually prove it in a more general context. But in a punchline, why is it prefix free? Because this piece 0, 1 only occurs in the end of a string. So you can use that to distinguish the end. Okay. But we'll explain that. We'll go over that in more depth in a little bit. But before doing that, let me ask you a question. Why are prefix-free encodings useful? Actually, let me also say that this prefix-free notion of prefix-free encoding is not just something theoretical. They're actually used all the time in all kinds of practical applications, especially in data transmission. You don't have to wait to do decoding, because if you have prefix-free property, it's really helpful. So often people use that in practical systems. Yeah. No, we could, but when we changed the encoding, right, Z to S bar, we duplicated every string, every element, right? So every 0 became 0, 0, every 1 became 1, 1. We artificially made sure that 0, 1 will never occur, right? So it can happen. Like if I take the encoding of 5, it is 1, 0, 1. But we changed it to 1, 1, 0, 0, 1, 1. So there is no 0, 1 anymore. Okay. So why is prefix-free property useful? It is useful for the simple reason that it is very easy to come up with representations of more complicated objects if you have a prefix-free encoding. So let me make it formal. Suppose we have a prefix-free encoding E from some space of objects 2, 0, 1 star. My claim is that if I have a prefix-free encoding from objects to strings, then I can immediately get representation of or encoding of lists of objects. So define E bar from theta star. So theta star, you should just think of as a list of objects. If I had integers, Z star would just be an arbitrary length list of integers, like, maybe to 2021, minus 10, minus 11. That's a list of integers. If I have a prefix-free encoding, I can get a representation for lists very easily. That's the claim. How can I do that? Well, if I have a list, let me call it theta 0, theta 1, theta 2. Okay, let me not use theta, that's confusing. A0, A1, A2, up to some AN. Yeah. So this is a list of objects, maybe integers or numbers, even whatever you have. I'm saying you have an encoding, prefix-free encoding of these objects. Now I have a list. How can I get a representation for these guys as binary strings? Any suggestions? Just concatenate, right? Which is what we did for rational numbers. I'm just going to concatenate these things. then E bar is a valid encoding. Okay, so this is the power of composition, right? Saying once you have a prefix-free encoding, you can get encoding of lists of objects from that space, and after that you can do recursion and things like that. Okay. Any questions about this? All right. So let's just make sure that our intuition is correct, and let's prove this theorem that E bar, this encodings of lists of objects, is actually a valid encoding. How can I prove this? Well, the proof is a bit of a mouthful, but the intuition is somehow clear, which is, we'll prove by contradiction. Okay. So we are only saying that it's a valid encoding, right? So if it is not a valid encoding, what should happen? There must be two objects, X, which is in theta star, Y, which is in theta star, two lists which are colliding in their representations, right? That's the definition of an encoding. If you're saying it's not an encoding, that means there is a collision. There are two things where X is not equal to Y and E bar of X equals E bar of Y. Okay. And we can say X maybe is the list is X0, X1, X2 to Xn. Maybe Y is, let me actually write it slightly better. I have these two things, and the encoding we're building is pretty simple, right? We actually, let me maybe draw it differently. Okay. So we're getting the same final string, right? So this is E of X0, this is E of X1, all the way up to E of Xn. Right? When we concatenate them, we are getting the same string from X and Y. But the individual pieces, they need not be the same. Encoding of Y0 might not exactly match with the encoding of X0. It's only when you concatenate them that you're getting the same result. Okay. So maybe let's say you had something like this. Okay. So this could be E of Y0, E of Y1, and so forth. When you concatenated them, you got the same thing. And we want to say that this actually cannot happen because E is prefix free. Right? So any ideas on how to, what's wrong here? Why can't this happen if E is prefix free? Yeah. Exactly. Right. So this picture, even though it's a bit of cheat, you can see the answer is kind of in the picture, right? If x0 and y0 are different, then one of them has to be the prefix of the other, right? Which is not possible because E should have been a prefix-free encoding. You kind of start, these two strings are the same. If this is shorter than this one, then that's bad because one is a prefix of the other. Okay. So let's kind of expand on that. Which contradicts. So that's the whole idea of the proof. And let's make it formal. So we know that the pair x and y are different. Okay. So let's say there exists an index I where xi is not equal to yi, and well, let me just write it differently. Let I be first index where xi is not equal to yi. Right? So maybe x0 is actually equal to y0, x1 equals y1, but at some point the two lists must be different. Okay. So if this is the case, then why is this? Why are we done then? It's the same argument, right? If x0 is not equal to y0 from this picture, like one of them has to be prefix of the other because they cannot be the same things. The same, you can use the same argument pushed up, right? Let I be the first place where they're different. Then you say, well, have x0, x1 to xi minus 1, then xi, and so forth. When I do the encodings, these two must match up exactly. Okay. Because all of these are equal, they're exactly matching. And now you have something different. This is E of xi and E of yi. Can they be the same length as each other? Xi is not equal to yi, but we know that when I stack them together, when I concatenate them, you're getting the same string. But can these two be the same length as each other? Yes or no? Well, we should have E of xi should not equal E of yi, right? Else, right? So if they're the same length and the two can equal, then these two should match up, which is a contradiction to E itself being a valid encoding, right? Else E of xi equals E of yi, which is a contradiction to E being a valid encoding. Okay. On the other hand, otherwise, you could have, maybe the length of the encoding of xi is less than the length of yi, which is also bad, right? Because this implies that e of xi is a prefix of e of yi. So this is saying, okay, the picture maybe it doesn't look like this. It looks something like this. But since the concatenations are the same, xi should occur as a prefix, which contradicts e being prefix-free. Contradiction to e being prefix-free, right? And the final case also you can do similarly. So in this scenario, you have the encoding of yi is a prefix of the encoding of xi. This is again a contradiction. To e being prefix-free. All right. So again, when you write it down in words or formally, it seems a lot more convoluted, but the basic picture is the same. That is that you have these encodings when you put them all together and getting the same string, right? That's the thing that we're trying to show cannot happen. And if it happened, like somehow, somewhere, you should have some kind of mismatch like this, which would contradict e being a good encoding or e being a prefix-free encoding. All right. Any questions about this? Yeah. Yeah. Right. So imagine, let's think of x0 and y0 being different, and the lengths are the same, right? But we know that the total strings, when I concatenated them, they're matching. So they should be matching kind of bit by bit, right? So they're matching bit by bit and they're the same length. So kind of I'm putting the stop at the same, cutting them off at the same point. So then what I'm left with will be the same string. So imagine you have like two sort of, strings, two tapes, they're matching P. Okay, so all this looks good, but I actually cheated somewhere. Can anybody point out where I cheated? There's a bug in my proof. If I wrote it in my assignment, I would not give myself, full point. Where did I cheat? It's a small bug, again, yeah? Exactly, right? So, why should there always exist an index like this? What can happen, is one special case is if maybe I have x0, x1 up to xn, right? And y0, y, this is x. Y is the same at every point. and then you added some symbols, right? I could have something like this. Maybe my first list is 1, 2, 3. The second list is 1, 2, 3, 4. Right? So then, technically speaking, there is no index I where they're actually different. Right? It's just that one is shorter than the other. Okay? Right? Make sense? I mean, this could happen, but then clearly the encodings cannot be the same, right? This is kind of, we just have to argue that this might not be the case. Not possible because then E bar of X would be shorter than E bar of Y. Okay, it's just an annoying case that if you want to be technically correct, then you have to write it down, kind of cross out all your T's. But the core of the argument where we're using the prefix-freeness is in this picture. Okay, any questions about this proof? All right. But as I keep saying, as I said again in the last lecture, throughout this course, definitions are more important than theorem statements than proof. So the most important thing so far today should be the definition of prefix-free encoding. And then the statement that if I have prefix-free encoding, then I can get compositions very easily. All right? Okay, so far so good. But this could be a much today about nothing if prefix-free encodings do not exist. Now, for integers, we could get prefix-free encoding. But when I do this, let's say I follow this process to get encoding of, let's say, rational numbers, C by Q, was a new encoding prefix-free? What do you think? No, actually, it's not necessarily prefix-free. So warning, maybe I'll use red color for warnings. Cells need not be prefix-free. Yeah. Let's see. We have 0, 1 and 0, 1. Maybe you're right. Right. But yeah, but E bar itself need not be prefix-free because just by definition you're concatenating things. You're right. Okay. So this is good, but it still doesn't let me compose things, right? If you've done any programming, you probably made list of lists, right? And then you made maybe lists of lists of lists. You create an object in Java, let's say, which is, maybe has some kind of list of elements. And then you create an object which has these as its children objects, right? So at some point, you have to be able to compose without any restriction. How do we actually do that? How is Java able to do it automatically? How is it able to get representations of objects, nested objects, much better? Okay. The reason is that you can convert any encoding to a prefix-free encoding, right? So do prefix-free encodings actually exist? Right. Okay. So let's take a 5-minute break and when we come back, we'll see that if there is an encoding for any object, then there is a prefix-free encoding. And we can do this in a mechanical way. Give me an encoding, I'll use that in a black box way. Just make a function call to that previous encoding and give you a way to get a prefix-free encoding. All right, so let's take a 5-minute break. When we come back, we'll see how to get prefix-free encodings from all encodings. All right, let's start. The reason, going back to the question from earlier, that why was I doing this more complicated encoding of rational numbers and integers and so on? The reason is that you can use that trick more generally. So in particular, here's a way we can use the same technique to convert any encoding to a prefix-free encoding, right? So suppose E from theta to 0, 1 star is an encoding. Then define a new encoding as follows. If you give me an element, let's say, maybe A, I'm going to write down the sort of steps in computing this guy. I'm first going to compute the original encoding of the object. Some encoding, it might not be prefix-free, it could be some encoding, like, for instance, let's say you started out with the unary representation of integers. I can convert that into a prefix-free encoding also. How can I do that? I'll do the same trick, which is I'll first compute the encoding and then replace each 0 with 0, 0, each 1 with 1, 1, and then add 0, 1 at the end. Okay, so I made everything prefix-free now. I just duplicated things so that I'm never going to see the string 0, 1 in the original encoding. And I added 0, 1 to mark the end of the new encoding. All right. So, well, claim is that then PFE is a prefix-free encoding. Okay. Very cool, right? Because we now don't have to be clever about getting prefix-free encodings. We do, we don't have to be clever about getting encodings or representations for lists of objects. Everything is sort of mechanical now. Give me an encoding, I'll first make it prefix-free, and then I'll concatenate. And then if you ask me to make new representation of lists of things, I'll do the same thing again. I'll convert it into prefix-free, and then just concatenate them, and so on and so forth. Right? And this is what actually happens in many programming languages. A slightly more efficient version of this, but this is the core of the idea. Okay, so let's just maybe spend a few minutes trying to understand why is this PFE as defined prefix-free, right? So you take an element X, let's maybe you map it via E, and then you get a string which is B0, B1, B2 to B. Okay, so this is E of X, right? So then what is PF E of X? I'm going to do B0, B0, it's kind of duplicated. B1, B1, B2, B2. Okay. And the reason this is prefix free is exactly the same as before. The string 0, 1 will never occur anywhere here, right? So 0, 1 can only occur at the very end, right? So if it's prefix, if there is a prefix, then they must be of the same length, which means that they are the same encodings actually. Does it make sense? Any questions about this? Yeah. Right, no, but again, we duplicate everything, right? So even if my original encodings generated things which had 0, 1, when I pass through this, I'm going to replace each 0 with 0, 0, and then 1 with 1, 1, right? So you're basically, even if the original one had a 0, 1, it's going to be 0, 0, 1, 1 from now on, right? They can be 0, 1, but the point is that you cannot have 0, 1 in an even position. Okay. Yeah. X is a single object. Yeah. So this is for encoding of a single object. We are converting it into prefix free, and we can combine this with our earlier theorem or earlier method of using prefix free encodings to get encodings of lists of objects. All right. Any other questions? Okay. So let's let's actually see it in action. It's not just a theoretical thing. Okay. So if you go to the EdSTEM webpage, there's lessons and there's also workspaces. We won't be using that too much, but if you actually go there, whenever I can, I'll actually post some code for you to play with. You'll see things like this, where you click on it. Okay, there we go. So the Python code should load. So here I've implemented, just binary representation, right? I'm starting with natural numbers to strings. This just computes the binary representation of a number, and then the decoding just for us to do some checks, string to numbers. Yeah, maybe let's not, let's say I do 2022. Oh, I just had to run the kernel again. All right, and let's say I print. Okay, so this is the binary representation of the natural number 2022. Let's check if I actually got the right representation. I can do this. Okay, it's working, 2022. Right? So the decoding is just our check. And here I'm writing a function, prefix-free, which takes an encoding object, right? Any function which does encoding, and then gives you a prefix-free encoding version of it. The decoding also, it takes a decoder and gets you a prefix-free decoder from that, meaning a decoder for the new PFE. Okay, it's also very simple. If you don't know Python, it's fine. It's just something which takes a function as input and returns functions as output. Okay, it's kind of returning handles to functions. And what it's doing is exactly what we said, right? Maybe I can do some fancy stuff here. No, we do it differently. Okay, cool. Okay, so the PFE, we said, you compute the encoding, replace each bit, each 0 with 0, 0, each 1 with 1, 1, and then you concatenate. And that's exactly what I implemented here. I compute the encoding of my object. I replace each one, I duplicate each bit, right? L of I is the corresponding bit position. I duplicated it, and then I add 0, 1 at the end. That's what it's returned, right? And the PF decode is just given a proper PF encoding, I can decode. And it's easy because I'm just going to ignore the last two symbols, which are just 0, 1 that we added. And then I need to kind of extract only the even position ones. Because I duplicated everything, I extract only, like if it was 0, 0, 1, 1, I say take out 0, take out 1, and I will use the original decoder on 0, 1. Okay. So that's what this is doing. Decode L of J for J in even positions. All right. And then this is valid thing is just checking if you actually have a valid encoding, right? 0, 0, 1, 1 are encoding as a special form. Every bit has to be repeated twice, and then you should have a 0, 1 at the end. It's kind of a cross check to make sure that you don't run it on bogus inputs. So the input can be any encoding function and decoding function, and the return will be prefix-free versions of those. Right? So I'm going to run that using my integers to string encoding and my string to integers decoder. And so, do you guys have any favorite number? Okay, let's. Okay, I should print. So this is the prefix-free encoding of 1984. Right? You can see everything is repeated, and then you get a 0, 1 at the end. You can also try, let's say 2022, get this guy, and let's check whether or not we are doing the right encoding. So to do that, we can do decoding. Okay, it's working. So I computed the encoder string AA, which is this string here, and I'm going to do the decoding 2022 back. So far, so simple, right? Nothing fancy. But now we have the power of composition, right? Let's actually see it in action. I'm going to use this to represent lists of integers as single binary string, right? And where did that go? That was very simple, right? We just concatenated the prefix-free encodings of the individual elements of the list. And that's what this code is doing. It takes as input a prefix-free encoding mechanism and then computes an encoder for the list. I just join the different encodings of the objects in the list. And the decoding is just for our sanity check, and it kind of works the same way. All right. And let's see it in action. Okay, tell me some list of numbers. 42, okay. How about 1936, 1984, 2012, 2022, 11. Okay, this binary string here is the representation for this list of numbers. Isn't that cool? Just this binary string. There is no marking saying, okay, here's a comma, here's like the length of the list, nothing like that. Just this binary string. Let's check whether or not it's correct, right? If it's the actual list, everything went through correctly. Then when we do the decoder, we should get back the actual list, right? It worked. Okay, so I just gave this string as input to the decoder, and it gave me back the list. Okay, you can, maybe, let's say I add in 7, maybe make the first one 13. Let's say LL. I don't know if you can see, but the binary string changed a little bit. When I run it, I get back the list again. Okay, so if you ever wondering how things are stored on your computer, this is how, right? Everything is a binary sequence. Run the binary sequence, even though there are no markings, no special symbols, nothing, you can get back complicated objects on. All right, yeah. We have a decoder for the single object, and then we're kind of to make everything sort of recursive, we're making sure that we get a decoder for the new encoder we're getting, right? So I started with an encoder decoder, I got an encoder and decoder. Okay, and if you're really crazy, this is in the workspace, so I encourage you to go and play with it and just compose it again, right? Get an encoder for lists of lists. It just had to do the same thing here, except instead of n to s and s to n, you would feed the same thing to itself, right? Does it make sense? I don't want to do that because if I do that, even for a list of 2 things, it's going to take up going to do a big string here, but you can do it if you want to. Right, so for instance, let's say, if I want to get representation for lists of lists, I'll first do so I have a representation for list to strings and a decoder string to list, but they need not be prefix free. So I need to make them prefix free. Okay. And then I need to make lists of lists. So L of L to S, S to L of L. Okay. Now these two are going to be ways to encode lists of lists to strings. Okay. So you can keep playing this game again and again. In fact, you can just bore yourself to death with it. All right, if you want to. Okay, so I don't want to do that in this class, but all of this is available for you to play with if you want to. And you can also see them in the lessons portion if you go there. It should also be there. All right. Okay. So what did we do so far, right? So we said we can compose representations. Give me a representation of object, I can get representation of more and more complicated things. So an image is a list of numbers. A matrix is a list of lists, right? It's kind of 2-level higher up. You start with a number, you make a list of numbers, that's a row. A matrix is a list of lists that basically you have rows, right? You can represent each row as an element of the list. And then image is exactly that. You can keep going. So the conclusion from this is that we can represent integers as binary strings. This is very simple. We probably saw, you saw this long time ago. But what we learned in the first 2 lectures shows that you can even represent lists of integers. Okay. And lists of integers, right? So for example, I can say 1, 2, 3, which is a list, 4, 5, maybe 7, 8, 9. Okay, this is a list of lists. I can write down a single binary string, which denotes this seemingly very complicated object, right? And these things are essentially like, matrices, images, and whatnot. Okay, so that's how every image at the end of the day just becomes a binary string. All right. Any questions about this? Yeah. So that's an excellent question. So let me, I was hoping one of you would ask me that, because there's some real, it can teach an entire course on how things are represented. It's very, very important, right? So in the ideal world, you might just be happy with this, right? But there's some properties that you actually want to satisfy in practice. So you start with this basic mechanism and then build a few things on top of it, right? So let's say, properties of encodings, right? So one thing people really care about is error tolerance. Okay, so our representation is very good, but it's not particularly tolerant to errors. If I flip a 0 to a 1, it might completely change the list that you're trying to decode. Okay, and in practice, basically, you try to do some encodings which might be more tolerant to like bit flips. All right, that's very important. You might wonder, why bit flips occur. They're relatively common. I mean, on the global scale of things, even cosmic radiations can cause bit flips. Okay, there's actually a video on YouTube in the Veritasium channel. I encourage you to watch it if you want to, where an election outcome was changed because a bit was flipped. So you want some kind of error tolerance along those lines, and that's something you can just teach a whole course on that. The other thing, which is very important as well, is efficiency. Okay, there's a reason why images are not exactly stored in this representation, because we have some prior knowledge about the kind of images that we see, and we think that if you change the representation, you might end up with shorter strings. Okay, so efficiency is another place where you might exploit that. And just as a side remark, our conversion of encodings to prefix-free encodings. How efficient was that? Right? So we had a black box, like, I give you an encoding mechanism, I convert it into a prefix-free encoding mechanism, right? The good thing about it was that you didn't have to be clever about this conversion. It's just like one function called, and then you duplicated everything and added 0, 1, right? So the length of PFE of X was basically, you started out with the original string and duplicated it. Okay, so this is the length of the original thing. So somehow, if your original representation had 100 bits, your new representation is 202 bits. So in some sense, you're basically kind of investing 50% of your space on just maintaining this property. Okay, which is good enough for our purposes, but you can streamline this much better. 50% wastage of hard disk space is a huge deal, right? If I have 128 GB and I store everything this way, it's only going to be 64 GB of space. Okay. And if you want to, the textbook actually describes a way to do it where can get PFE, where PFE bar is of length okay. So you don't lose a factor of 2, a small additive amount. Okay. So I start in the original encoding and I add some number of symbols, like basically logarithm of it. It's like 2 times log, let's say. And you get back a prefix-free encoding. It's not actually too complicated. Just to spoil the idea, you can look at the textbook for more details if you want to, but it's not the focus of this course. We're not caring too much about the efficiency, mainly about whether or not it's possible. Okay. Any other questions? All right. So that's kind of what I wanted to say about encodings, but let me end with some history and what's to come in the next lecture and so on. And as I said in the last lecture, we're going to only open this box of representations only once. Now that we know that any complex can be represented as binary strings, we're going to take that as granted from now on. We're never going to look at prefix-free encodings or opening this box and so on again. From now on, every input will just be a binary string. Because if you think, oh, I don't care about binary strings, my input is images. Okay, well, I just convert it to binary strings. Right? So that's why we did this. But let me ask a question, which is, can we represent real numbers as binary strings? So far, we are doing really well, right? Pretty much anything we can think of, we are able to represent as just binary strings. So what is there a limit to this? Can we represent real numbers as binary strings? You might have seen this before. What's the answer? Yes or no? No. Okay. Depending on where you put the qualifier. So this is equivalent to saying, can we get a 1-to-1 map from real numbers to 0, 1 star? Okay. So what do you think is the answer to this? Yeah? No. Right? And it's one of the most fundamental theorems in math due to Cantor in 1876. He showed that there does not exist an encoding of real numbers to binary strings. Okay. So we're not going to prove this in this lecture, but if you want to know more about it, you can look at the textbook or come to one of the office hours, and we'll be happy to provide more details about it. Okay. But let me just say a few things about this statement, because we're going to see things like this statement much later in the class. This is an impossibility result. It's saying you cannot even represent all real numbers as 0, 1 star binary strings, which are what computers take as input. Okay. Maybe now it seems okay, it's just okay, whatever, right? It's just a math statement. But back in the day in 1876, when this came out, this was it caused quite a bit of a scandal, to put it mildly. For instance, here were some of the reactions of the leading mathematicians or philosophers from then. So when Cantor published it, Wittgenstein, who is a famous philosopher, called it utter nonsense, right? Laughable. Okay. Kronecker, you might have heard of Kronecker. He's also a very important mathematician. He called Cantor corrupter of youth. Okay, but the cake or icing on the cake goes to Henry Poincaré. Poincaré from Poincaré conjecture, one of the 7 millennial problems, $1 million problems. Famous geometer, right? Very important figure in mathematics. He said Cantor should be banished from mathematics. Once and for all. Okay. It's really funny if you think about it now, but back in the day, Cantor's result was so unthinkable, right? And in the same vein, we'll come back to what Turing did, right? He showed a similar impossibility result, which was just as revolutionary and kind of made people really miserable for a while to accept it as a fact, right? And the proof technique is in the end similar, okay? But gradually, things improved. In 1925, this was around 1876 when the result came about, but it took around 50 years for people to really appreciate what Cantor did. Hilbert said, Cantor opened a paradise for us. To go from corrupter of youth to opening a paradise takes around 50 years in math. All right. So you can read the proof in the textbook if you care about. Okay. That's a bit of history, funny history. But we'll get back to this kind of statements that you cannot have certain objects throughout this course. All right. To summarize our discussions, we can build encodings of objects, of lists objects from encodings of objects. Okay. And as a result, going forward, we will assume that inputs, we are going to talk about computation. Okay, this problem is solvable, this problem isn't solvable, right? Often we should think of problems to have some semantic kind of, the inputs have some semantic meaning, right? It's an image as input. Here's a graph as input. Here's a string, is a text. Here's Shakespeare's, textbook. That's your input, right? But we will assume that inputs are from just 0, 1 star. We can always do this because we know there is a way to do it, right? Or we can also switch back and forth in their natural form. Okay. In some sense, when we want to define the most powerful model of computation, when we're trying to define things, prove impossibility results, we're going to assume things are from 0, 1 star because we can always convert it to that. But if I ask you to give you an algorithm, okay, I tell you, here's a graph, find me, like, let's say, maybe a cycle in this graph, right? Maybe you saw this algorithm in CS32, CS180, and all those things, right? You don't start with, okay, here's the binary string, right? Now I have to dig into, okay, how do I decode the edges? And then how do I run an actual breadth first search on top of that and things like that? We're not going to do that. We'll switch between those two to make our jobs easier, okay, depending on what is convenient for us. But we have this foundation that we can always do this in a rigorous automated way, okay? So any questions about this? All right. Without explicitly opening the box of going from one to another. Okay. So in the next lecture, when we come back, we'll start with taking inputs, which are just binary strings, and then build models on top of that. And this is not just an, again, as I'm stressing again and again, it's not just an artificial model. We don't have to restrict ourselves to specific forms of input. You can always assume they are coming from 0, 1 star strings. Okay. All right. So next lecture, we'll talk about computational models, which takes binary strings as input.